Okay guys, well welcome to the first video of our third unit, which is bonding and molecular structure. Today we are going to be looking at C.3.1 of our substandard, which is to investigate the observable characteristics of elements, ionic, and covalent compounds. Okay, so by this point you should be somewhat familiar with your periodic table of elements, but just for review, elements are the smallest unit of matter that maintains its unique properties. They can be monatomic, meaning 1 unit, or diatomic, meaning 2 units. The key thing to pull out of this is mon, right? Mon, or later on we will see mono is 1, and atomic. So it's monatomic, mon, 1 atom. Diatomic, di meaning 2, atomic, 2 atoms. Okay, so diatomic elements are naturally occurring in the universe in pairs of 2 atoms. They are from the periodic table of elements. So we have I2, Br2, Cl2, F2, O2, N2, H2. And there is a simple mnemonic device to remember your diatomic elements, which will be useful to you as you progress throughout this course. I brought clovers for our new home. Of course, the elements are all located on your periodic table of elements, and you should be somewhat familiar with them by now. Here is some models of the diatomic elements. These big ones that look like balloons stuck together, they are called space-filling models. And it's kind of to give an idea of what is actually, what they kind of look like when they're stuck together as diatomic elements. There's emergence that happens. They merge in the middle. But also to give another perspective, we have something called ball and stick models. So the balls are the little spheres and the sticks are these lines that connect the 2 atoms together. So if there is only one line, like in iodine, bromine, chlorine, fluorine, and hydrogen, if there's only one line between those 2 spheres, that means that that is a single bond. However, diatomic elements also have the potential for 2 bonds called a double bond, 1, 2, double. Think of double scoop ice cream. Or 3 bonds, 1, 2, 3, called a triple bond. Think of a triple-decker bus that you see in movies on touring in Europe for whatever reason. So there are 2 atoms which are connected. They are diatomic and they're bonded together, and that is a natural occurrence in the universe. So we have atoms and ions, which are single units of matter. Atoms are the single units of elements. Hopefully that makes sense by now with the diatomic and monatomic explanation. Ions are atoms or subunits of ionic compounds which have gained or lost extra electrons through chemical reactions. They carry positive or negative charges. Ions are single atoms which have extra or less electrons, atoms with a plus or minus. And this plus or minus will be seen oftentimes accompanied with a number, and it's a superscript. So a superscript is above and to the right of the chemical symbol, and a subscript is to the bottom right of the chemical symbol. So you'll be familiarizing yourself with that too throughout the course. Polyatomic ions. Poly is basically like more than 1. So you're having more than 1 atoms which have joined together as units, okay? And then they have charges on them. So multiple atoms as a singular unit which have extra or less electrons than in their atomic state. They are subunits of ionic compounds with a plus or a minus. And again, that plus or minus is going to be the charge number. It's going to be written at the top right-hand corner of the chemical symbol. And it is oftentimes accompanied with a number, but not always. Ionic compounds have extra electrons or missing electrons within their subunits. And this is because they can be positive or negative. Again, we're going to get into this a little bit further. Ionic compounds are compounds which combine from ions which have transferred electrons. They have full charges of a positive and negative ion. Electron clouds tend to be more one-sided, and that's because of the full-on charge of the negative. Ionic compounds form when a metal and nonmetal bond. Ions form when these metals and nonmetals separate after bonding. So before the reaction happens, which is right here between this sodium and this chlorine, they are existing as atoms. But once this purple electron from the sodium has been transferred through this reaction, they now exist as ions. But because they're still stuck together, they are an ionic compound. Now, at any point that these two go their separate ways, this will be a positive ion, and this will be a negative ion. It's also important to note, if you remember from your atomic structure, so we have neutrons and protons which exist inside the interior of the nucleus, and then the electrons exist within the quantum electron cloud, okay? So what is happening here is because the amount of neutrons and protons within the nucleus of the sodium did not change, but the only alteration was for the electron to leave. What happens is that you have an additional proton then in the center. Even though it's not really extra, it looks as if it's extra because there's no electron, a negative, to balance out that positive charge anymore. So it's become a positive. It's become a positive ion. And the same thing is pretty much happening over here. The protons and the neutrons have not changed inside the nucleus. However, there's an additional electron to compensate for that negative charge. So because there was one electron transfer, this is a sodium +1. This is a chlorine -1 charge. So again, later on you will see charges that are associated in superscripts with numbers, but because this is a single electron transfer, it's only a plus and a minus sign. There's no number associated. So covalent compounds are when electrons are shared between two atoms. Okay, so covalent compounds which share electrons to stay together. All covalent compounds are still technically atoms, but they're stuck together. Covalent compounds exist in two types. Covalent compounds are two or more nonmetals which join together to share electrons. They can also be they can also be a nonmetal plus a metalloid, but we will look again more at this in the next lecture portion. This will be the next video. I'll cover that. So we have polar covalent, in which one atom is partially stronger than the other atom. Here we have an example of a polar covalent image. And you see this little squiggly looking D. Some of my kids have said, I think that looks more like an 8 or, yeah, but what it is it's a delta. It's a lowercase d for Greek, and it's read as delta. So this is delta negative and delta positive. Now, if you remember, an electron is always represented by a negative charge. So what the delta means is that it's partially negative. The electron's more likely to be found over here, and it's partially positive because the electron's not as likely to be found on this side where the hydrogen is. So that makes it a polar covalent. The electrons are shared unequally. And also, it's important to note that a lot of times in chemistry you will see a blue and red color coding to indicate polarity within compounds and molecules. So when you see the blue color, it's pretty much always color coded as negative, and the red is pretty much always color coded as positive. Now the second type of covalent compound is a nonpolar covalent, where each atom is equally as strong. So the electrons are shared equally. Okay, this is not a diatomic element. It's just showing an example of a nonpolar covalent bond, because in organic chemistry, you get a lot of carbons which are involved. I mean, basically, organic chemistry is carbon chemistry. So I think that's why that was chosen. If you are looking at both of these images, you'll notice that there's kind of like a gray matter area. That's to represent kind of the emergence of the electron clouds. Okay, so there's equal probability for the electrons to be here as there is here, where there is unequal probability for the electrons to be here as opposed to here. It's going to be more likely, there's a larger radius of electron cloud here, so it's a one-sided kind of cloud. There's going to be a lot more chance, a lot more probability for the electron to be existent over near the oxygen than there is the hydrogen. So just to recap, ionic and covalent, I really like this as a summary slide, because you can see the arrows that are equally the same size, and they're both showing that there's some kind of pull, right? But you can see the emergence of the yellow and the orange here, and then that the chlorines are sharing them as a diatomic element equally. This is an example of a covalent bond. So the bondings are shared equally, or the bonding electrons are shared equally between the two atoms, and there's no charges here. This is nonpolar covalent, okay? And there's still atoms. Anytime it's a covalent bond, there's still atoms. Okay, remember, ionic bonds are between ions. Covalent bonds are between atoms. Atoms, atoms, ions, okay? And you'll be able to tell the difference, because the only thing you really have to remember is that ionic ions, okay? It's pretty much the same word. Now, polar covalent bonds, again, remember I told you about the color coding. When you see blue, you're going to see a negative charge associated with that somehow, if it's color coded correctly. So we have a delta negative, so it's a partial negative and a partial positive. Notice that the partial negative is a thicker arrow, it's more exaggerated, so there's a stronger pull on this electron from the hydrogen, okay? And that's why it's a blue area. And you can see that the clouds merged, right? But there's a greater probability that the electron's going to be existent over here. Then it's important to remember that electrons aren't stationary. They're constantly moving around within their little mini quantum universe, okay? So polar covalent bonds are bonding electrons shared unequally between two atoms. There's partial charges on the atoms. Notice atoms, two atoms, and then this is ions, okay? So there is a complete transfer of one or more valence electrons in ionic bonds. In ionic bonds, there is a complete transfer of one or more valence electrons. There's full charges on resulting ions. And notice that these two are not merged together. They're basically held together by electrostatic forces. You can see where this electron used to exist within the sodium ion, and then it's vacated. There's like a little circle empty space, right? And the yellow has come over here to exist as an addition to this chlorine, giving it a negative charge of 1, and then leaving the sodium with a positive charge of 1. And because nobody wants to write anything extra, if they don't have to, it's not necessary to write the 1 in there. You can just write the plus or minus if there's only one electron transference. When you get more than one electron transference, then you will have to note the number as a superscript. Here, this is a better option to see what a superscript will look like. It'll be in the upper right-hand corner of the chemical symbol. Okay, guys. Thanks so much for listening. Just one last thing. This right here, I want you to notice that around each chlorine atom here, that there are 8 electrons, and that's called the octet rule. In the valence shell of atoms, all atoms want to have 8 electrons so that they can be like noble glasses. They want to be kings or queens in their own right. Okay, so that's why this guy was so happy to get its 8th electron. and he wants to stick around and kind of like be the cool guy, right? That's part of this exchange. So just food for thought. We're going to be making sure that we can fulfill those 8 electrons anytime we're bonding. As long as you're looking at periodic trends, you're going to be wanting to fill up those 8 electrons in the valence shell when possible. So thanks for listening for the ionic and covalent bonding and our little chat about elements and ionic and covalent compounds. I hope this was positively informative. Ha ha ha. But yeah, we will be picking it up from here next lecture day, and I hope you guys are able to answer all the questions on your worksheets. Thanks.